Okay, let's talk about acid-base strength. So, aside from the fact that you were told to memorize an arbitrary list of acids as strong acids, right? HCl, HBr, HI, HNO3, H2SO4, HCl4, HCl3, right? So, you had to memorize these. And I don't know if you've ever stopped to wonder why you had to memorize these. Like, why are these strong acids versus others? So, let's talk about that. First, uh, let's talk about binary acids. A binary acid is just two elements, right? It's a nonmetal bonded to hydrogen, hydrogen being one of the elements, okay? So what makes an acid strong is its ability to ionize, right? The more it ionizes, the stronger the acid is, okay? So let's consider two atoms, hydrogen bonded to an oxygen. So how well this acid ionizes is based on the weakness of the bond, right? And so the more polar the bond, the more likely it is to ionize. So when I say bond polarity, remember we're talking about electron distribution. Oh, that's too big. Right? So let's say we have a really polar bond. Right? The electrons are definitely more attracted to the nonmetal, and that's generally going to be the case. But it's to the point where when the bond is very polar, it's a weak bond. And the hydrogen is likely to be pulled off by something else like a water molecule. All right, so here comes a water molecule passing by, and if there is an attraction here between the water and that hydrogen, if that attraction is strong enough and if this bond is weak enough, it's a tug of war. Well, what's attracting more? Is it the oxygen pulling this hydrogen, or is it the bond with this nonmetal? And that's essentially going to determine how likely it is that the H plus will ionize and form hydronium. Okay, so the stronger the bond is, the less likely it is to ionize. Yes, Ron.
I'm just a little bit curious. In that case, how come HF is a weak acid when it's like really, really, really polar?
Okay, that is a good question. That's our prime exception. So, what do you know about fluorine? Just spout out anything you know about fluorine. A very electronegative, yes. What about its size? Oh, very small. So when it's very small, the electrons involved in the bond to get closer to the fluorine nucleus, more so than chlorine, bromine, iodine, fluorine. So because it's very small, bond strength is high. Doesn't dissociate easily. At least it doesn't dissociate as easily as you think it would, right? You would think that, oh, it should be a strong acid, but it is not. Okay, so that's our prime exception. But in comparing, so we know that there's a list of HCl, HBr, HI. So those are your strong acids. Those are very polar. They have very polar bonds. Okay, and thus high dissociation. So let's take these two examples here. These are binary acids, right? They're binary acids because they're only made up of two elements, right? One is sulfur, one is hydrogen, right? One is selenium, one is hydrogen. So which of these bonds is going to be more polar, the bond between hydrogen or the bond between hydrogen and selenium? Well, let's look it up. All right, hydrogen, its electronegativity on your periodic table, depending on what year, is 2.1 or 2.2. Sulfur is, I don't remember what sulfur is. Everybody grab periodic table. I want to say 2.5. Ah, 2.5. Okay, so you have this. But then you have H2SE, right? So selenium's electronegativity is 2.4. And it's actually a bigger atom. So between these two, we've got more polar bond in H2S. That bond polarity means that the hydrogen is more likely to dissociate off of H2S than it is H2SE. So now, mind you, I'm not saying either of these is a strong acid. That is not what we were saying. But I'm saying since they're both weak acids, but compared to each other, H2S will ionize more than H2SE. Right? And that would be reflected in Ka values. Right? So if I had a Ka for H2S of like 3 times 10 to the minus 7th, then the Ka for H2S would be something smaller than that. Not dramatically, but something smaller. That makes sense? Okay. All right, so that's the first type of acid. That's a binary acid, okay? Let's talk about an oxoacid. Oxoacids, these are the nonmetals that are bonded with a bunch of oxygens, and the hydrogens are bonded on the periphery. So you would recognize oxoacids as, HNO3, H2SO4, anything with a nonmetal, a bunch of H's and a bunch of O's, right? So the strength of an oxoacid is based on something else, right? It's kind of based on comparing the number of oxygens that are present. So here we have HNO3, right? So there is resonance involved in HNO3. Right, we've drawn this maybe a couple times back in our bonding unit. We consider this shape to be trigonal planar, right? Okay. All right, and then HNO2 would look like this. Right, so there's a double bond. There's not really resonance here because the double bond cannot necessarily be averaged between both oxygens because both oxygens are not equivalent. Okay, so when you have everything, when you're comparing acids and when everything is constant between them except for the number of oxygens, the element with more oxygens equals a greater amount of electronegativity. So HNO3 versus HNO2, the three oxygens offer up more electronegativity, which destabilizes the bond with H, right here. So this bond is polarized more than this bond because the two oxygens do not have the same drawing power for electrons that 3 oxygens do. Think of them as magnets. 3 magnets versus 2 magnets, pulling electrons all towards the center. The one with 3 oxygens pulls all electrons inward towards the center or more, and that means since hydrogens are on the periphery, the electrons are pulled away from the hydrogen, making that bond less stable, more easily polarizable. So hence, HNO3 is a stronger acid than HNO2, but this is something you already would have known because you have a mental list of strong acids. But this is why. Okay, so with oxoacids, when there's more oxygens, that's going to be a stronger acid. And if you look at your list of strong acids, what do we see? H2SO4. You don't see H2SO3. HClO4, HClO3, but you don't see HClO2. Right? Okay, so HNO3, you don't see HNO2. Okay? So it's the ones with the maximum number of electrons, those polyatomic ions in their acid form, those are the strongest. Okay, so that's one aspect of oxoacid strength. All right, when there's more electrons, more oxygens. Okay, what if it's not the number of oxygens that is different? What if it is the central element? Okay, so if you had comparing two, this is not too small for me. If you're comparing two oxoacids and they both have a common number of oxygens, but the only difference is the central atom, like here versus here, then by similar rationale, the central element that has greater electronegativity has the weakest bond. The hydrogen to oxygen bond is the weakest. So something like H2SO3 versus H2SeO3. How these two acids are identical except for the central nonmetal. Which one of these is the stronger acid?
H2SO3?
Yeah, the one with the higher electronegativity. Sulfur has more electronegativity than Se. Okay? Does that make sense, guys? Think about what's going to make a hydrogen pop off of an oxygen. It's if that bond has been weakened, and the way to weaken the bond is to polarize it, to make electrons pull towards one side versus the hydrogen, and the hydrogen, there's not much left hanging on to the hydrogen. Okay? All right, so if you need to compare acids based on their formulas and make predictions about their strength, that's how you do it. The logic is different depending on the type of acid. Is it a binary acid or is it an oxoacid? Okay. And the thing is, once you memorize what the strong acids and strong bases are, you can kind of use that knowledge to help you make predictions, right? You can, in a question like this, you can use the knowledge that like this is a strong acid, so you should know it's stronger, and to help you explain why, well, then you fall back on the number of oxygens, right? You know that this is a strong acid, but this is not. So what is the reason why? Well, this has a greater electronegativity than nitrogen does. Okay. But if asked, your response should not simply end at, oh, nitrogen is more electronegative, right? The second part of explaining that is because it is more electronegative, it destabilizes the hydrogen that is bonded to the oxygen, making it a weaker bond, and thus H is more likely to come off. All right, so it's realizing that hydrogen is more electronegative is halfway there, but you have to finish, you have to follow through by explaining what makes something more acidic. Okay, the fact that the H is more likely to come off because the H is now a weaker bond. All right, remember complex ions? Remember how we have transition metal ions that kind of get surrounded by water and form complexes, right? We've drawn this one many times, tetraamine copper, right? So we did a lab. Our first lab was hydrolysis / Ka lab, where you tested a bunch of salts and a bunch of weak acids, and you had to determine the Ka, and you had to, solve for the Ka. Now, we compared copper, and I think we did iron, and maybe we did one other, but I know for sure we compared copper and we compared iron. So iron was +3. So iron is going to look very similar to the, you know what? I'm sorry. I got to change this. This was a bad example. I'm going to change these to waters. All right. Sorry. Copper, water. Okay, so, because we're talking about the hydrated. And technically, this is a complex. The formula of this is CuH2O4 2 positive. Based on what you know about complex ions, how many waters should attach to iron? We should have 6 on there because the general idea is that it's twice, the coordination number of ligands is twice the charge. All right. 1, 2, 3, 4, 5, 6. And the formula then would look like this. Right? Okay, so why is that acidic again? Remember that this complex, the reason why anything is acidic is because it dissociates an H+. So this would undergo this type of reaction. Your H2O count would go down by 1, your charge would go down by 1, and you would produce an H+. That's why that's acidic. Now, the pH of the iron that we tested was at least a pH unit lower than the pH of the copper. The copper hovered around 4, if you recall, like maybe like 3.9 or 3.8, and the iron was like 2 point something, 2.2 or something like that. Why the difference? They both transition metal ions. What would cause a hydrogen on the iron complex to be more likely to come off compared to the copper? Think about what we just discussed. It's not necessarily electronegativity. It's magnitude of charge. Right? +3 charge. What's going to attract the oxygens in water more? +2 or +3? +3. If the waters are attracted more strongly, they're going to be pulled inward at a, more strongly than they would in copper. And if they are pulled inward, that strains the bond that oxygen has to the oxygen and destabilizes it much in the same manner. So, higher charge, stronger attraction between water and central ion. Weaker H2X. Oops, it's not X this time, it's O. Making that a stronger acid. Okay. Did you notice that when we talked about acidic ions, the cations, what 4 were they? Cousin alpha, right? Copper, zinc, aluminum, and iron. Look on the periodic table. Look at the block. Look at 3D. Where are cousin alpha? Transition metals, but where are they? Are they early transition metals or late transition metals? Towards the right side, right? Zinc, copper, aluminum, iron. We don't really see acidic behavior so much with scandium or titanium or vanadium. What's the difference between the left side and the right side of the periodic table in general?
The right side has more
Let's not pay attention to the electron count itself. What else is there more of on the right side? Protons. Nuclear charge. Right? So what attracts electrons more? What attracts anything more positively? Zinc or copper or scandium and titanium? The right side. Higher nuclear charge, stronger attraction for water. Water more likely to break. How come we don't address 4D metals or 5D metals as complex ions that are acidic? What is the difference between the elements at the top of the D block versus the bottom of the D block? Very generally, what's the difference? Versus top versus bottom? Size. And what effect does size have on strength of attraction? Weaker. Oh, so the bigger ones that are weaker don't attract as strongly. If they don't attract as strongly, they're not as likely to destabilize the hydrogen that is bonded in water. Okay? So there are trends here at work. Okay. And lastly, so this last section is not going to be tested, but we'll talk about it since we're here because it does parlay into what we've been discussing. So oxides, in general, you need to know that non-metal oxides are acidic. Example, SO2, gas released from smogs in factories, right? Reacts with moisture in the air and ends up forming H2SO3, right? So we form acids from non-metal oxides that are dissolved, that are released into the air. Okay? That's just one example. Metal oxides are basic, and we actually did discuss this back in Unit 3. For example, Na2O, right? Na2O, it dissolves an oxide in water. But first, what's going to happen is this. Right? We form the oxide ion. But the oxide ion in water is basic because it's going to hydrolyze and form hydroxide. So that's all we really need to say about that. But not a focal point. I don't think that's been covered on AP exam for a while. Okay, that's kind of what I wanted to talk about as far as acid strength.